You got it? I'll begin. Dear Heavenly Father, excuse me. We thank you for this day. Thank you for these students who pray with us today. Help us to glorify you in what we do, Lord Jesus. Amen. I was going to thank him for no CFAWs, but I had to check first. Are we safe? Are there any CFAWs among us? No? Okay. Okay, so let me just remind you a little bit. I'm going to go through some of these proofs here. The content, all right, of a non-zero polynomial with integer coefficients is the greatest common divisor of the coefficients. All right, so that's what we define the content to be. For example, 3x plus 6 has content of 3 because 3 is the greatest common divisor of that. You can easily see that if you have a monic polynomial, in other words, the leading coefficient is 1, then that's going to be what's called a primitive polynomial because it has a content of 1. A primitive polynomial is simply one that has content 1. So one of the theorems that I didn't prove last time but I mentioned was that the product of primitive polynomials is primitive. Here's the proof of that. So if you have g of x and f of x and z of x that are primitive, then towards a contradiction, suppose their product is not primitive. All right? Then if p is a prime divisor of the product, right? In other words, if it's not primitive, that exists, and right? Then you can consider the reduction of these polynomials mod p. And so that again, this means to reduce the coefficients modulo p. And so if we take then 0 is equal to the reduction of this. Why? Because it's a multiple of p, right? So any multiple of p is 0 mod p. And so 0 is this, right? So we have f of x and g of x. The reduced ones are what? These are non-zero things, and yet their product is 0. Well, that's troubling because we have proved previously that z mod p of x is an integral domain, right? Well, I'm sorry. So since this is an integral domain, I should say, this equation here implies that f of x is the reduction of f is 0, or the reduction of g is 0 mod p. So it follows that p divides f of x or g of x, which means that either f or, p divides f of x or g of x. I didn't need the either there. So consequently, one of them or the other of them, or both I suppose, has what? Has p as a divisor, which means its content is not 1. They're not primitive. That contradicts our assumption that they're primitive. So in short, the product of primitive polynomials is primitive. This reduction is part of a more general trend here. If you have a ring homomorphism, you can always induce a natural homomorphism from the polynomials over the ring to the polynomials over the homomorphic ring just by mapping coefficients like this, right? So just take this polynomial, a(n) x to the n plus da 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 plus a1x plus a naught, and map it to phi of a(n) x to the n, and so forth and so on. You can prove that this is a homomorphism. So every homomorphism of rings induces a corresponding homomorphism of polynomials with those ring coefficients. That's what we're using in this primitive argument. So here's the theorem I mentioned last time. If f of x is a polynomial with integer coefficients, if it's reducible and it's reducible over q, then it's also reducible over z. And I'm not going to go through this proof in class. I'll let you read it. But basically, the nuts and bolts of this is just to use this primitive notion and work through it. It's not particularly exciting, so I'm going to move along. All right. But this I did want to go through the proof of with you guys. So here's another theorem. Suppose you have a polynomial that is with integer coefficients, has positive degree, and you can consider the reduced polynomial again, as we've talked about. You take the coefficients and change them to their corresponding modular coefficients, mod p. Then here's the punchline. If the reduced polynomial is irreducible over zp, and the degree of the polynomial is equal to the degree of the reduced polynomial, then the original f of x is irreducible over q. This is pretty nice because this means we can trade a problem of how do you factor something in Z for how do you factor something in Z mod P? And if we're successful in showing it's irreducible, well, that's really nice, because questions mod P, sometimes you can just figure out by just plugging in numbers, a finite set of numbers, right? If you try to plug in all the integers, we'll be here a while, right? So here's the proof. Suppose you have f of x reducible, suppose you have a polynomial with integer coefficients, degree better than 1, and furthermore, suppose that you have the reduced polynomial is irreducible with matching degree, all right? And then towards a contradiction, we're going to suppose that f of x is reducible over q, right? The theorem is the opposite of this, so if we can prove that this produces craziness, then we win, right? Anyway, so there's a technical statement of proof by contradiction. But anyway, hence by theorem 3.5.11, there exists h and g with this. Why is that? It's irreducible, right? And I'm saying f of x is reducible over q, right? The previous theorem says then it's also reducible where? Over z. Okay, so that's the main, I think, use of the theorem I didn't show the proof of to you just now, is right here. In my opinion, is right here. So notice we're saying reducible over q, and we're trading that for the existence of polynomials with integer coefficients that reduce it. That's not the definition of reducible, that's using the theorem that I have not proved, but have indicated. All right, so the previous theorem. So we got f of x is g of x, h of x, and of course, what does that say about the degree? Well, the degree of g and the degree of h is going to be less than the degree of f, right? If it's actually a reduction. So using the homomorphism of the reduction homomorphism, we have that that f is equal to the product of its reductions, right? Now, here's the deal though. If this reduction happened to have like p, or a multiple of p, it's its leading coefficient, it would lose a degree in the reduction, right? So like, you could have something like, we could have a quadratic which becomes, so here's in z of x, right? And if we apply the reduction homomorphism, say mod 3, then this is equal to what? Just this, right? The leading coefficient's no longer at second order. So in general, when we use this reduction homomorphism, we could lose degree. So that's why I say that the degree of the reduced polynomial is going to be generally less than the degree of the original. And that's true for g and for h, all right? But what else do we know? We're assuming what? At the outset, we're assuming that the degree of f is equal to the degree of its reduction, right? So check this out. I have degree of g, the reduced g is less than or equal to the degree of g. That's less than the degree of f because we're, remember, assuming that f is equal to gh. But the degree of f is equal to the degree of the reduction. Likewise, we have here the degree of this is less than the degree of h, which is less than the degree of f. Again, these are equal. So what do we have? We have the degree of the reduced g is less than the degree of the reduced f. We have the degree of the reduced h is less than the degree of the reduced f. What that means then is that f bar is reducible in ZPX. But that cannot be, because why? As my little brother used to say, cuz be why. No, more simple reason. We assumed it's irreducible, right? So you can't assume that and then have it's reducible. This is madness. Consequently, garbage in, garbage out. The garbage was that f of x was reducible over q. In fact, that cannot be. So there's the proof. Eventually I'm going to remember to plug this stupid thing. All right, or change the power settings. But anyway. Can't give you guys time to breathe. Grief. What's going on here? All right, so it's cramping my style. Come on, computer. So anyway, my point to you is, yeah, I'm going through this pretty fast, but this proof is actually very, very easy to understand. And the one I skipped is not much harder, really. It's just you have to go through the details. Now, let's see here. one of your homework problems, in fact, exercise 29 that's due Monday, I guess, is to prove this guy. X to the fourth plus 1 is reducible in ZPX for any prime. And yet, it's irreducible over Q. So you have the joy of adding that example to the discussion. I'm going to show you this example, though. This is really interesting, this one here. So here we have f of x is 3/7 x to the fourth minus 2/7 x squared, 9/35 x plus 3/5, all right? So what's, I can, since we hate fractions, at least I do, I can't speak, I guess I shouldn't speak for you, but I personally hate fractions. So I'll get rid of them by multiplying by 35. That gives us this, nice integer polynomial. And now we can work with the tools that are given to us for integer polynomials, right? Integer coefficient polynomials. So the irreducibility, I mean, I think you guys can agree with me. If this can be reduced, then so can that, and vice versa, right? So if you take a polynomial and you multiply a rational polynomial and you multiply it by a non-zero number, if the resulting polynomial is reducible, then the original rational polynomial is reducible, and vice versa. Okay, so working mod 2, what's the deal here? Reduce this h mod 2, we get, see what happens? Mod 2, 10 is gone, 15 becomes 1, right? 9 becomes 1, 21 becomes 1. So this rather ugly looking thing, mod 2, is just x to the fourth plus x plus 1. This is already really neat, I think. And well, if you plug in 0, you get 1, right? And if you plug in 1, you get 1. So by the factor theorem we proved the other day, it has no linear factors, right? Now, you can't immediately extrapolate from that this is irreducible. Remember, the theorem is only good for order 2 and order 3, right? If a polynomial of order 2 or order 3 has no zeros, then it's irreducible. That was a theorem that we had the other day. So, but this is order 4, right? So we're out of luck. But on the other hand, since it's got no zero, that means it has no linear factor, right? But it can still have possibly a pair of quadratic factors, right? Now here's the really neat thing, I think. If you think about what are possible quadratic factors over z2x, there's a finite number of them. So think about this. x squared plus 1, x squared plus x, and x squared plus x plus 1. I think that's it. I mean, can you guys think of any other quadratic polynomials of order 2, order 2 polynomials over z mod 2, which are not in this list? Have I missed anything? I don't think so. So obviously, some of these have zeros, right? Like x squared has a 0 if you plug in 0, 0. And let's see here, if you plug in 1 into this, it's got a 0, right? And also 0. It says 2 zeros, right? In fact, this is x times x plus 1, so x equal to 0 and x equal to 1 are both zeros of this guy. So, but the x squared plus 1 also has a 0, right? Because 1 plus 1 is 0. You tell me that? Yeah, good. So, process of elimination, got a 0, got a 0, got 2 zeros. How about this one? If you plug in 0, you get 0 plus 1 is 1. If you plug in 1, you get 1 plus 1 plus 1 is 3, which is 1. So this is the only possible factorization. Why am I saying that? If you had a factorization of the quartic into two quadratics, right? If one of those quadratics had a 0 in it, guilt by association, right? That would then imply that the quartic also had a 0 in it. Just think about what a factorization means, right? So it follows the only possible thing that this can factor into is this guy, right? And so Gallian says do long division. That's fine. But that seemed like a lot of trouble to type up, so I instead did this. Sorry, it's not a really good reason. It is the reason. So x squared plus x plus 1 times x squared plus ax plus b equal to that. That's what I'm looking for. Apparently, this is the only thing that can be a factor, right? In fact, this would also have to be what? Think about it. It would also have to be the same stupid thing, wouldn't it? If you think about it. But anyway, I just multiply that out. It gives you this system, right? And then for this to be equal, we have to have matching coefficients, and you can easily see that those equations are inconsistent. So consequently, there is no way to factor it with that quadratic factor, which shows that x to the fourth plus x plus 1 cannot be reduced. It's irreducible over z2. And then by the theorem that I just talked you guys through, that implies that h of x is irreducible over q, and consequently, the original f of x is irreducible over q. So this is kind of a neat idea, right? You just look through, I mean, when you're faced with a quartic, you can actually enumerate the possible quadratic factors over a finite field and just check and see if any of them work. Of course, this is less fun when we use Z3, right? But usually when you have these kind of problems, you start with Z2, see what you can do with Z2, right? All right, now we come to, I would say, a big gun. This is Eisenstein's criterion. Check this out. F of x, a n x to the n, a n minus 1, x to the n minus 1, blah, 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 plus a naught. And anyway, a polynomial with integer coefficients, all right? Then, if there's a prime p such that p does not divide the leading coefficient, all right? However, p does divide all of the other coefficients, except, one more thing, p squared does not divide the constant term, right? Given those conditions, I would say rather weird conditions, right? Like, why on earth did Eisenstein think of this? I don't know. He was a student of Gauss. Maybe it rubbed off. I don't know. I think he also died under the age of 30. All these great 19th century mathematicians. Math was very dangerous in the 19th century, really. Anyway, or maybe it was just the 19th century. Let's see here. Anyway, so given all that, then f of x is irreducible over q. Whoa, that is, I mean, check that out. Like, look at how much trouble we just had proving this quartic was irreducible over q. It took work, right? This says if you check these three boxes, ding, 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 then it's irreducible. This is fantastic. Now the proof here is by contradiction. It's not especially exciting. You can read it. I will go over proof another day, most likely, which is from, it's named, anyway, it's on page 300, but we're not there yet. So, but we'll get back to the proof of this. There's an elegant proof that's given later, so why not just show you the elegant proof? Anyway, here's an application of it. 13x to the 7th plus 2x to the 6th plus 4x cubed plus 18x plus 2. I'm going to use p equals 2. So 2 does not divide 13, right? But 2 does divide 2, 4, 8, and all the zeros, right? 2 divides 0. Does anything not divide 0? No, 0 divides 0 too. 0 is 0 times 0, right? So 0 is, yeah, whatever. Anyway, so 2 does divide all of the coefficients that are non-leading, all the non-leading coefficients, right? And does 2 squared, which is 4, does 4 divide 2? No, does not. You're like, but 2 divided by 4 is a half. What do you mean? You know what I mean. So it's not allowed. Right, so of course, 2 does not divide 4 in our language. So Eisenstein's criteria has been met, and we find that this f of x is irreducible over q. Yeah, right? Of course, Eisenstein's criteria doesn't work for all examples, but it does create some very nice examples. It's not hard to see that using Eisenstein's criteria, you can create polynomials of arbitrary high order over the rational numbers, which are not reducible. Or not, let's see, how did I say? Oh, here it is. Yeah. Yeah, they're irreducible. Here's a really pretty application of this. If you look at s equal to 1 plus x plus da 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 plus x to the p minus 1, and then I multiply by x, I get that, right? So then if you take the difference of s and x times s, you get what? Lots of canceling, right? The x's be canceling, the x squareds be canceling. Only x to the p and the minus 1 survive, right? So formally, we get that 1 plus x plus da 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 plus x to the p minus 1 is equal to x to the p minus 1 divided by 1 minus x, right? Factor 1 minus x out over here. All right, so this actually is sort of a formal heuristic for what's called the pth cyclotomic polynomial. Blah. So it's not hard to prove with Eisenstein's criterion that the pth cyclotomic polynomial is irreducible over q. here's a proof that you'll find in pretty much every abstract algebra book. I'm not sure who did this to start with, but somebody did it. It wasn't me, but this is the argument you'll find in all books. So if you look at the pth cyclotomic polynomial evaluated at x plus 1, all right, let f of x be that, then see what happens here? So you use the formal expression, plug in x plus 1 for x. What do you get? You get x plus 1 to the p minus 1. Then downstairs, you get x plus 1 minus 1, which is super nice, because it's 1 over x, right? Then upstairs, you binomial this thing. X to the 1 plus p by the binomial theorem is this. And then you subtract 1, so the 1's cancel, right? So then what happens? These x's reduce. So you have x to the p minus 1 plus, well, anyway, let me scroll down here a bit. So cleaning things up a bit, we have f of x is x to the p minus 1 plus p times x to the p minus 2 plus plus p. We'll check it out. The leading coefficient is 1. P does not divide 1, right? If p is a prime greater than whatever you like, I mean, 2 or greater, let's say. Any prime, really? So 2 does not divide 1, but the p will divide all these coefficients. When you look at the structure of the binomial coefficients, they all have a multiple of p in them, all right? And so all of the non-leading coefficients are divisible by p. P squared does not divide p. By Eisenstein's criteria, this is irreducible. But then if you suppose that the pth cyclotomic polynomial was reducible, then that would imply that f of x was equal to g of x plus 1 times h of x plus 1. You can easily multiply these out and see that that would provide a reduction of f of x, which is impossible by Eisenstein's criterion, what we already argued. Consequently, the pth cyclotomic polynomial is irreducible, which again is pretty cool because it gives us a polynomial of essentially arbitrary degree. Well, prime minus 1 degree, I suppose. Sorry if I shined you in the eye with a laser. That is irreducible over the integers, which is pretty cool. Oh, I guess over q, fine. All right. At this point, well, all right, one more. So here we have the next theorem. This is very useful. And I really should, you know what, I'm going to put this away. I'm going to do it. I know you guys prefer to me to not do this. So we got far enough. I can do it now. Oh, curses. I was wrong. We didn't get far enough. I tell you what, I'm going to prove that one, though, by hand-to-hand combat here. I thought it said lightning for a second. I was like, why would you have a button for lightning? It doesn't seem right. Ah. I stopped saying, where's my laser? Start saying, where's my taser? Is no allowed? It's no allowed, yes. Okay, so theorem. Let f be a field, and suppose you have a polynomial over the field. Then the ideal generated by p of x is a maximal ideal. In polynomials, if and only if p of x is irreducible. Did I already prove this? I don't think I did. I think I showed you an example of it, right? I showed you that Rx mod x squared plus 1 was a field because x squared plus 1 was necessarily irreducible. We looked and said, oh, there's no linear factor because that would imply real applies imaginary, so forth. I do think we did that last class. All right, here's the proof. All right, so suppose F is a field, and let's suppose that this is a maximal ideal. All right, what's that mean? Then this is a what? It's not equal to the 0 ideal, right? And what else? It's a non-zero proper ideal, and let's see here. P of x is not equal to the whole thing, right? So how do you get the polynomial? How do you get the ideal generated by a polynomial to be the whole polynomial ring, or how do you get the 0 ring, the 0 ideal from the generation, either from the polynomial being 0 itself, or from it being a constant, right? The units, any unit in the ring of polynomials will generate the whole ring of polynomials. So basically, these two conditions just rule out P of x having degree 0. Or basically, these two conditions imply that P of x is non-constant. All right? So, suppose that P of x was equal to g of x times h of x. All right? Suppose that's a factorization of P. Then if if j of x, right, is an element of the ideal generated by P of x, what's that say? That implies that j of x is equal to P of x times something else, right? Because it's in the ideal generated by P of x. What's that say? Oh, but P of x is what? Right? So let's see here. What's that say then about the j? J of x is what? This is an element of what? The ideal generated by g of x, right? So if j of x is in the ideal generated by P, it's also going to be in the ideal generated by one of its factors. But we took an arbitrary point, right? So what's this give me? This tells me that the ideal generated by P of x is a subset of the ideal generated by g of x. So then what? All right. Hence, just to keep the score of things here, the ideal generated by P of x is a subset of the ideal generated by g of x, right? Which of course is a subset of the whole thing, right? So what are the two cases here? Right, so either if I'm going to do the opposite case, but yeah, you got the second case. If the ideal generated by P of x is equal to the ideal generated by g of x, that's one possibility since P is maximal, right? Could be that the ideal, but if this is the case, then what? H of x equals to 1. Well, I don't think I can quite say that. I mean, that's the right kind of idea. I mean, you would agree then I can say g of x is an element of P of x, right? And then what? so that implies that g of x is equal to q of x times p of x for some q, right? But on the other hand, we know that p of x is what we said before, g of x times h of x, right? So this tells us that the degree of g is what? This tells us that the degree of p is what? Excuse me, I got it. I didn't say it, but I wrote it wrong. Greater than or equal to, right? So if I have this, then by the properties of the degree function, the degree of g of x is greater than the degree of p of x, right? And here, this says the degree of p of x is what? Is greater than the degree of g of x, right? How can this be? A less than b, b less than a, less than or equal to both cases. So the degree of g of x is equal to the degree of p of x, right? So what does that say? That's exactly the that's the result we want, right? Because you go back up to here, we've just showed that the degree, in this case, case 1, right? This case 1 has said that the degree of p is equal to the degree of g. What's that make the degree of h? That makes the degree of h 0, right? But also, so basically what that means is h is a non-zero constant, which is, by the way, a unit in this ring. Consequently, we're just finding that if you factor p of x, one of the factors has to be a unit. Right? That implies then that p of x is irreducible. So this implies the degree of h of x is equal to 0. Therefore, h of x is equal to u, and a unit. So therefore, p of x irreducible. That's case number 1. What's case number 2? Yeah, the case you wanted me to do to start. What did you say? It's what? Right. The whole shebang, right? And so if that's the case, what that implies that g of x is equal to a unit. It's the only way you can generate all polynomials is to have a unit there. I have more details in the type notes there, but and there you go. Again, if that's a unit, that implies p of x irreducible. Whoa. So a corollary to this, right? Corollary f of x mod the ideal generated by p of x is a field given p of x irreducible. I've stated that a weird way. Usually I would say assume p of x is irreducible, then this is a field. Okay? And I'm assuming f is a field here. So that's corollary 3.522. All right. I'm not going to write out these examples which are following. They're too lengthy. Come on. Okay, there we go. An example, if we look at the finite field Z2 and the polynomial x cubed plus x plus 1, you can prove that that's irreducible because it's non-zero for when you plug in 0 or 1. So the fact that it's non-zero, it's cubic, shows it's irreducible. And so this is a field. So Z2x mod this cubic polynomial is a field. And Gallian's got a partial table for the multiplication. It's a field with 8 elements. But one way you could look at it, another way you could look at that, right, is just in terms of the representatives. And so basically the rule for simplifying the representatives is that x cubed is equal to minus x minus 1. I mean, that's how I think about this thing personally. Now, mod 2, that's also equal to x plus 1, right? Because we can add 2 of each. And so like here's a sample calculation. If I multiply x times this in this field, then you just basically distribute. And instead of having an x cubed, I got an x plus 1, right? And you just regroup stuff like that. Or here's a more interesting one. X times x squared is x cubed, right? But that's x plus 1. So anyway, any multiplication you do, you can always bring it back to one of these fundamental 8 things in this way. And I don't know, that's kind of neat. We didn't have a field with 8 elements before, but now we do. So I think that's actually kind of interesting, right? Because we know Z8's not a field, right? Because 2 times 4 is 0, but 2 and 4 are 0 divisors. So it's not a field. It's got things that are not units. But there's something else of order 8, which is a field. This thing. You can also look at this x squared plus 1 over, that's supposed to be z3x. I'm missing an x there, right? This is irreducible over z3. You can easily check, plug in 0, you get 1. Plug in 2, you get what? 4 plus 1 is 5. 5 mod 3, 2, right? Non-zero. Plug in 2, what did I do? 0 gives you 1, 1 gives you 2, and 2 gives you 4 plus 1, 2 again, right? So anyway, all the possible values of x squared plus 1 are non-zero. Consequently, it doesn't factor. It's irreducible. So this is a field. So I think it's a fantastic way of constructing fields and things, right? This is definitely something I don't feel like writing out today. This is the unique factorization theorem for integers, polynomials over the integers. So any polynomial with integer coefficients you can factor into a unique product of irreducible polynomials of degree 0. That's that's basically just the ordinary prime factorization of integers. And then here's your interesting polynomial pieces. And this will be unique up to the ordering of these things. So if you had some other such factorization, then you could show basically that these b's and these c's were the same things, just reordered. And the p's and the q's would have to be the same things, just sort of reordered, and possibly multiplied by plus or minus 1 because those are the units in Z. The proof in Gallian is, pretty easy to read. It's 3 stages. Again, it uses content. I'll let you look at that. All right. Man, I was going to spend 20 minutes on that stuff. What happened to us today? It's all my fault. All right. So, it brings us to today's material. It's okay. I still got 20 minutes left. Let's see here. So three things, right? So Bradley, you should be happy. We're going to address your question from last lecture finally. You have, in an integral domain, you have 3 kinds of things you can think about. Well, at least these are 3 things you can think about. Associates. 2 numbers in an integral domain are associates if there's some unit that connects them. In other words, b is equal to a times a unit. All right? One thing. Another thing we can define, a is irreducible if a is not a unit, and whenever a is equal to c times d, then C or D is a unit. All right. So basically, there's no non-associated factorization, so to speak, right? So like associates, this would not show that B is not reducible, right? I mean, B can be equal to A times U, and that wouldn't show that B is not irreducible. I mean, irreducibility is the question, can you take A and can you split it apart into two things, neither of which are a unit? Okay? This is really the same thing we were just thinking about in polynomials, isn't it? In fact, this squares well with our definition of irreducible polynomial, doesn't it? This is the same definition I just gave for irreducible polynomial, the class lecture. A prime, A not equal to 0 is prime if A is not a unit, and if A divides BC implies A divides B or A divides C. Now, if you look at different algebra texts, some will teach students to find the prime factors of a polynomial. Others will teach you to find the irreducible factors of a polynomial. It's like, but wait, they're different. But the thing is, no, they're not. In the context that we teach children polynomial division, we're working in, polynomials over a field. Polynomials over a field are an integral domain. One of the things we prove in this lecture is that every irreducible is prime, and every prime is irreducible in an integral domain. So the difference between irreducibility and primeness, if you will, is only going to be seen outside the context of an integral domain. All right? And also, the other thing that we're going to hopefully get a better understanding of as we study this lecture is the notion of a unit, right? We're going to get a little bit better way of thinking about what are units. Let me get to that because it might help you with your homework. So we can get a lot of traction just from looking at this one example. Z adjoin the square root of minus 3. Okay, so this is a particular, generically speaking, square free means that, it could be 35, but it couldn't be 50. 50's got a square in it. So if that square is in, then it just muddies everything. So we say square free. Keep it simple. So check it out. 1 plus the square root of minus 3, right? It turns out if you set that equal to xy, that implies that x or y is a unit, all right? You can prove that 1 plus square root of 3 is irreducible. I'll prove that in about 5 minutes. Give me a minute. So on the other hand, you can see that 1 plus root 3 times 1 minus root 3, right? Root minus 3 is 1 minus minus 3, which is 4. That's equal to 2 times 2. Now, we're defining prime how? If, see, so here, if we have 1 plus, if we have 1 plus the square root of minus 3 divides 2 times 2, right? This says 1 plus the square root of 3 divides, is that true? Yeah. So 1 plus the square root of minus 3 divides 2 times 2, and yet this does not, that 1 plus the square root of minus 3 does not divide 2. Now that's not immediately obvious to me. Here's why. Suppose it did divide 2, right? Suppose that the product of this and that was 2. Then that would, if you multiply it out, that would give us this equation, which gives us that a minus 3b is 2 and b plus a is 0, which means a is equal to minus b, which means that 4a is equal to 2, so a is equal to 2/4. That's kind of hard to do in the integers. So 1 plus root 3 does not divide 2. Consequently, it's not prime. Right? Here's a number. It divides the product of these two numbers, and yet it doesn't divide either of the numbers. So it's not prime. And yet it's irreducible. Now, I haven't proved it's irreducible yet. Give me a second here. I'll do it. Before I do that, though, I must introduce something called the norm. Norm! Sorry, it's from another time. But anyway, this is not the norm. Nah, sorry, it's endless. In the sense of linear algebra, those axioms are gone. This is a different kind of norm. The new norm. Anyway, I'll stop. So let R be an integral domain. Any function from the ring of the integral domain to the natural numbers in 0, such that 0 maps to 0, is a norm. Well, that seems rather generic, doesn't it? I mean, goodness gracious. And it's a positive norm if it's positive whenever A is not 0. Okay, great. So how do we get a norm on Z adjoining the square root of D? Basically, I'm inspired by the modulus. So remember the modulus in complex, x squared plus y squared is the modulus squared of x plus iy, right? So that's also ZZ conjugate. So if I think about the conjugate in this, I think that, you know? So if I multiply these two things, that gives me a squared minus db squared. But you got to be careful. This could be negative. So you put some absolute values around that, and that gives you what we call the norm. Now, of course, this is just a definition. I didn't have to prove it. And that's not a proof of it. It's just a motivation for it, all right? It's inspired by the modulus squared of a complex number. And there you go. That's the norm in this wild world of integers adjoin the square root of D. And check it out. These are the properties. 0 maps to 0, and only that. This is the super useful one. The norm, it's a multiplicative norm. The norm of a product is the product of the norm. And this 3 is amazing. So the units, all right? The units in Z adjoin square root of D are just the ones with norm 1. That is wonderful. That means all we have to do is analyze the equation a squared minus db squared equal to 1, plus or minus 1 really. If D is negative, we can drop the absolute value because minus D becomes a positive, so we have the sum of squares. But this gives us a specific prescription of how to find all the units in at least this kind of space, right? And so I'll let you guys prove 1 and 2. Those would be like some of the most fun homework that you've done this semester. I'm a little short. Well, no, I'm okay. I think I can. To prove, I'll prove 3 for you at least. So to prove 3, suppose that x is a unit, right? Bad algebra. Yeah, bad algebra. CFA. Just pounding a CFA down. Let's say here. Get out of my classroom. No, sorry. X, if it's a unit, then x times y is equal to 1 for some y. But then n of 1 is n of x times n of y, right? But n of 1 we can explicitly calculate. It's 1 squared plus d times 0 squared, otherwise known as 1. So if you look at it, 1 is equal to n of x times n of y. What are the solutions of 1 is equal to number times number in the integers? One, right? The only way you can get 1 from the product of two integers is, I'm sorry, it could also be negative 1 times negative 1, but the norm is defined to be positive, so that's out. So there you go. That's 3. All right, so then I'll prove to you then, now that we have that, y was 1 plus root 3, 1 plus minus root 3 irreducible. Well, suppose it was reducible. 1 plus root 3, suppose there's a factorization of it, right? 1 plus root 3, squared minus 3, rather, is equal to x times y. Take the norm. The norm of this, missing one of these deals, is 1 squared plus 3, also known as 4. So 4 has got to be the product of the norms of x and y. Well, and if x and y are not units, then that means you have to have both of these be in 2, right? So then we are forced to find solutions to the equation a squared plus 3b squared equals to 2. That's what's required in order to have these being 2. No can do'sville. You can try different integer solutions to that. It's impossible to solve. It's pretty easy to convince yourself of that pretty fast, right? This, you can't have b be anything but 0. Otherwise, you'd have 3 here, and you'd have 3 plus something equals to 2. That's nonsense. So your only hope is b is equal to 0. What do you got? Then you got a is plus or minus. You got a is 0. That's no good. 0 is not equal to 2. You got a is plus or minus 1. 1 is not equal to 2. Then you got 2. 4 is not, and then it just gets worse from there. So through explicit case-wise consideration, you can prove that there's no solution there. Consequently, if you have 1 plus root 3 is equal to x times y, that must force either x or y to be a unit. Consequently, 1 plus root minus 3 is irreducible. Now, this would have been awful without the concept of a norm. Completely and totally awful. This example is a little bit trickier. We're short on time. I'm going to skip to the main result I wanted to share with you guys. Well, we'll do these next time. It's cool. But the thing I wanted to actually share with you guys, where'd it go? Here it is. This may actually be useful for your homework. Check this out. Let R be a commutative ring with identity. If A and B are associates, then the principal ideal generated by A is equal to the principal ideal generated by B. Finally, if R is an integral domain and I is generated by A, then any other generator of I is an associate of A. This is what I was using in the examples I've done to find the basic representatives of the ideal in the Gaussian integers. We took 2 plus I. What did I do? I multiplied by the units. 1 minus 1, I minus I. Those give me all of the known associates of 2 plus 2i, if you will. Those are the other possible representatives of that coset. Anyway, so, well, excuse me, those are the other, not all the representatives, but those are the basic representatives, let's say. Anyway, so the proof is here, but I'm out of time, so. Never enough time.